what are yantras, and then how it can be explored using graph theory and so on. So yantra is a Sanskrit word which means an instrument, a device, or an appliance. Like what in modern days we can say a yantra is right now what we are all using, a computer or a cell phone or a television. So these are all appliances, devices. And in ancient days they were using devices for various purposes. So all those devices were called yantras. And let me just minimize the screen. Okay, I think this is blocking the yeah, okay. So yeah, just one second. Okay. Is my entire screen visible, or is it getting blocked by the uh, window?
No, I can see everything. We're okay.
Okay, 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 yeah, okay. So yeah, so yam means to hold, and tra means that which liberates. So yantra, one meaning in Sanskrit is that which liberates, and to this we are for this meaning we are referring to some mystical diagrams which were used for various purposes like meditation, like for concentration, and like in different cultures, in Hindu culture also, some mystic diagrams were used for various purposes. Before we go to that, I'll just give you a glimpse of the different types of yantras that were used. Some astronomical yantras are some famous yantras we can see in places like Jantar Mantar in India, in Delhi, in Jaipur, where there are a lot of astronomical instruments that are placed, which were used for doing a lot of astronomical calculations, movement of celestial bodies and things like that. And surgical instruments were also called yantras, and machines or mechanical devices. Basically, all these come under yantras. But we are going to look at these geometrical drawings, which includes mainly some symbols and some shapes. Okay. So in the presentation, I have just put up some different types of yantras so that later on those who are interested they can go through it in detail. So astronomical yantras, surgical yantras, rasayana yantras are yantras which are used for preparation of medicines, and mystic diagrams. And here is also a note, this is something that I came across. This is the name of a text called Yantra Sarvasva, written by a person named Bharadwaja. So in this text, Yantra Sarvasva, Bharadwaja mentions about a lot of types of yantras, and some of which are as old as the yantras that were used in the epic Mahabharata. So yeah, so here are a few pictures of different types of yantras that were used. As we can see, this is typical uh, water, tank kind of yantras. These are astronomical yantras that are found in that we can see in Jaipur. This is a picture that I had taken when I was there in Jaipur, in Jantar Mantar. Sundials also form different parts of and different. It's one of the types of yantras, and these are the mystic kind of diagrams. As we can see here, there are a lot of geometrical shapes, and there are some mantras that are, or aphorisms that are written in Sanskrit. And here we see there is a magic square. Actually, these are numbers written in Sanskrit. This is 16, 6 and 8, 2, 10 and 18 and 12, 14 and 4. So this forms a magic square, and magic square was also one kind of yantra, and magic square was used in different civilizations. It was believed that the kind of numbers that we use in a magic square has got its own positive and negative effects. on the person who's using it. So this also comes under yantras, and this is also a type of yantras. Again, we can see it's a combination of some numbers and some specific kind of symbols. So this also comes under yantras. And magic squares, like I said earlier. Okay. So what we would be discussing is mainly we would be discussing these kind of yantras, and these colored yantras are some things, some images which are downloaded from the web, and this one is an image which I downloaded from a research article. So initially I'll just give you some different images of yantras, so that when we discuss about graph theory it will be more clear. So as we can see, there are different kinds of yantras, and but there is a similarity. We can see this kind of sorry, yeah. So we can see this green thing, this green boundary or this maroon boundary, and over here a yellow boundary. This is actually called Bhupura. So Bhupura is something that Bhu actually means earth. So this is the kind of basement, or I mean something of that sort that they give. And then usually in all the yantras there are circles, and then there are petals. So these are like flower petals, and then again there are circles, and we can see a lot of appearance of triangles and stars and hexagons. So and here there is a very famous yantra that many of us might have seen, especially in Indian homes. We'll see this. It's called Shri Chakra or Shri Yantra, and this is another type of yantra. Okay. So coming to graph theory is an interesting subject. Actually, it's something that is usually taught for undergraduate courses, but it's a topic that can be explored even at middle school. And in fact, unknowingly, we do a lot of puzzles when we are in schools, not knowing that it's a part of graph theory. So the beginning of graph theory is very interesting. Some of you might be already knowing there was a great mathematician by the name Leonhard Euler, and he was the originator of graph theory. So the story in short goes something like this: there were some islands in a place called Königsberg, and there were 7 bridges which were connecting these islands. So they had to make a parade, and they wanted to take the parade in such a way that it would go through each and every bridge exactly once, without going through the bridge once again, and it will be able to traverse through the islands. So this, how can this be done? That was the question that was posed, without going through the same path again. And this question was posed, and Euler took up that question, and in order to give his answer for that, what he did is he developed an entire theory on in mathematics, which is today known as graph theory, and that was the beginning of graph theory. So those who are interested to know more, you can just Google on 7 bridges of Königsberg, and you will get a lot of videos on YouTube and a lot of stuff over the internet about the history and story of this particular thing. Okay. So when we talk about graph theory, there are some terms that we need to understand. So I'll just brief through the terms. So let's say that these are 5 cities, 1, 2, 3, 4, 5. These are 5 cities or 5 towns, and let's say that these lines that we see, these are the lines that connect these 5 cities. So let's say that city 3 and 4 is connected only through one line. Let's say there is only one road from 3 to 4. Or if somebody wants to go from 3 to 4, they can even go from 3 to 2, and then they can go to 4. So there can be lines which are connecting 1 and 5 as well as 2 and 5, but let's say the towns are they are in such a way that there is no direct road from 1 to 5 or 2 to 5. So if somebody wants to go from 1 to 5, they have to go through 3 or 4 maybe. Yeah. So these cities are the points which are called nodes, or the cities are the vertices, let us say, or the vertices are the cities. So this 1, 2, 3, 4, 5, they are called nodes or vertices. And then let's say that this is another graph that I have just taken. So let's say that there is city A, B, C, D, E, F, and colored lines are the roads that connect city from, I mean, city A to B and A to F and so on. And these roads are called edges. Okay, and these edges, like from A, if we have to go to F, one way is we can go from A, B, C, D, E, F, or we can go from A, B, C, E, D, F, or we can directly go from A to F. So these different ways are called path. Different paths, for going from A to F. So whatever path we take from going from one place to the other, it's called path. And path is always through the edges. We don't go directly. So we can see that there is no direct path from B to F in this graph. So if somebody wants to go from B to F, they have to go from through A or through the other way around. So these colored lines are called edges. Then we have something called as degree of a vertex. So let me just try to draw something just to show that what's the degree of a vertex. Let's say that there is one city here, another city here, a third one here, and let's say a fourth one here. So if I connect these four like this, say connect it like this, and suppose, let me just do one thing. So just hold on, yeah. So let's say that there is one city here, another city here, a third one here, and a fourth one here. Let me just call the city A, B, C, and D, and I'm just connecting it like this. So there are four vertices or four nodes A, B, C, D, and the degree of vertex A is the number of nodes, or sorry, the number of edges. The number of edges connected to A. The number of edges connected to A is called the degree of A, or the degree of vertex A or node A. So we can say that there are two edges that are connected to A. So the degree of the vertex A is 2. Similarly, B, degree of B is 2, C is 2, and D is 2. But suppose we draw a line like this. So now the degree of vertex A has increased to 3, and the degree of vertex C has also increased to 3, because there are three lines which are connected, or three edges which are connected to vertex C. Yeah. And let's say that if there are four cities A, B, C, and D, and we want to and they are connected through these lines. Let's say there is this line from A to C, and this is one way. So now let's say that somebody from, let's take an example. Let's say a postman wants to deliver some letters in all these cities A, B, C, and D. So these are the four cities where he has to go and deliver the letters. But on the way, he has to travel through these paths. Or let us say that while he is traveling on these edges, he has got people, lot of people who are staying on these edges, and he has to deliver letters to all these people. So basically he has to traverse a path. He has to travel through a path which will take him through the edges, and if he has to make it really quick, he has to be very efficient so that he does not repeat, he does not travel on one path two times. So how will that postman find the most suitable path for him? So let's just take that example. So let's say that the postman decides to start from point B. So one option is he can go from B to C, and then let's say that he goes from C to D, and then from D to A, and then either he has to go from A to B or he has to go from A to C. But if he takes A to C, then he cannot go to this through this path, because if he has to go that, then he has to either go back this path or maybe he has to go through this path again, which is again a waste of time. So if he travels from B, if he starts from B, even if he goes down to C or if he goes to A, it's a waste of time for him. So the point is, if you start from B, you cannot draw this entire thing without lifting your hand, without lifting the pen. So let's say that he starts from point C, and if he starts from point C, maybe he can go from C to D, and let's say that he goes from D to A, and then he goes from A to C, and then he goes from C to B, and then he goes from B to A. So suppose somebody is starting from node C or vertex C, then he can actually draw this graph without lifting the pen. Yeah. So that means if a postman is traveling, he can travel through through all the edges without going back. So here this is one way of constructing. This is another way, because if you might have noticed, how I constructed this was, I went from C, D, A, B, and then from C I went diagonally up to A. So this is one way. So now here the degree of the vertex is 3, here the degree of the vertex is 2, here it is 3, and here it is 2. And when we started from this vertex 2, we could not traverse the entire path, but when we started from 3, we could do that. So this is some observation that which we need to keep in mind. Yeah. So we'll be discussing more on that. So let me just give another example. I'm reminded of an example which we used to give to our friends in school. That this particular figure, that is, if you have a rectangle and then or let's say a general quadrilateral, usually we used to draw a rectangle, and we had this particular this figure, this one, and then like this. So the question used to be, can we draw this figure without lifting our pen and without overwriting or without traveling through the same path again? And in school, I remember we used to cheat a lot in this. Either we used to take 1, 2, 3, 4, and 5, and then like this, and this, and this, and this, and maybe we would draw something like this and erase this particular part. So this is how we used to do this in school, because it was not possible to draw this particular graph. So now this is actually a question under graph theory. So let's slowly go to this particular image. We were here. Let's say that we have one more path like this from here till here, and let's say somebody wants to travel. So before we do that, what we are going to do is, we are going to, since we are interested in studying the graphs, we are going to count, or we are going to measure the degree of each vertex. So here the degree of this vertex is 3, because there are 3 edges which are connected to this vertex. Similarly, 3 over here, 3 over here, and 3 over here. Now somebody might ask, what about the point in between? Is this a vertex? Can we call this a vertex? Because we see a point. But in this case, we are not calling it as a vertex, because we have defined the vertices to be A, B, C, and D. We have said that there are 4 cities. So any point of intersection in between, we are not considering that as a city. It's just a crossroad, let us say. So we are not considering this as a node, this red point. So let's see if we can, if the postman can travel from any particular city, let us say city A, B, C, or D, and then he is able to go through all these edges exactly once, without without traversing the same graph again. So suppose he goes from D to A and A to C and C to D, and let's say this B and then C, but then we are left with AB. So no matter however we try, I mean you can take this figure and you can try it, but you will see that it's not possible to traverse through the all the edges such that uh, we don't go through the same edge twice. So let's take the next uh, figure which will lead us to the puzzle. So let's say there are two lines like this. Now let's see the degree of each vertex. So here the degree is 1, 2, 3, 4. So now there are 4 vertices over here. Here also there are 1, 2, 3, 4. So there are 4 edges which are connected to this vertex. So this vertex has got degree 4. Similarly, for every vertex the degree is 4. The degree of each of these vertices are 4. Now let's see if the postman can travel through all these paths. So let's say he starts from this point and he goes like this, and he goes like this, and maybe he goes like this and like this. Let's say from here, and he goes here, then he goes here, and then he goes here. Yeah. So he was able to traverse the entire path without going through the same edge twice. And if you might have observed, if I can just name this as A, B, C and D, 4 cities A, B, C and D. Our postman started from city D and he came back to city D. So which is like he takes his bunch of letters, he goes through the entire paths and then he comes back to his original place. It's not that he's starting from D and he is ending somewhere else, which if you see this earlier figure, this one where we started from one place, let's say we start from here, here and here, and then it went like this. So we were starting from C but we ended in A, but here we are starting from D and it goes and then finally it comes back to D. Yeah. So here also we were able to go through the entire path without traversing the same path again. Here also we were able to do that, but what is the difference? Here in this case, in the first case, we started from one city and we ended in another city, but in this second case we started from one city and ended in the same city. Yeah. So this is something that we need to observe. So I've just drawn those 4 figures over here. What is written in this blue circles is the degree of each vertex. So here we can see there are 2 vertices where the degree is 3 and 2 vertices where the degree is 2. Here we have all vertices degree 3. Here we have all vertices degree 4. Here we have all vertices degree 5. So let's just check this. This is 1, 2, 3, 4, 5. So there are 5 edges connected to one vertex, and similarly it's like this. So there are 5. The degree of this particular vertex is 5. And as we can remember, in this case we were able to draw the graph, but like I said, we started from one city and ended in another city. But in this case we started from one city and we ended in the same city. And in these two cases where the degree of the vertices were 3 and 5, we could not start and end in the same or different cities. We could not traverse the entire graph without repetition. Yeah. So the reason I'm giving these examples of cities and postmen is because this is something that we do in our everyday life. Let's say that we have to go through a certain, we are given some tasks. Let's say that we have to buy a few things, and we go out with our bike. we try to think of the optimal way in which we can go and do this entire thing and then come back without repeating any path. So this is something which we all use in our daily life, unknowingly though. So this is something called as an Eulerian circuit. An Eulerian circuit is nothing but a path which it's like you start from city A and then you go through all the edges without repetition, without lifting your pen, and then come back to city A. So if you start from a city, you come back to the same city, then if you are able to do that, then it is called an Eulerian circuit, or it's also called as an Eulerian graph. Yeah, so it's as simple as that. And I mean, it just to show that this was a case of Eulerian graph or an Eulerian circuit, because we were able to start from a city and then we were able to come to the same city. And in an Eulerian graph or an Eulerian circuit, we can see that the degree of all the vertices is always even. It will always be even. Yeah. Okay. And then there is something called as Eulerian path. So Eulerian path is the same thing except for one condition, that you can start from a city and you can end in any other city. So if you start from city A, you can end in any other city. It's not important that you come back to the same city. So for this, we can see that in an Eulerian path, we will have either 0 or 2 odd degree vertices. So the number of odd degree vertices, that is, if the degree of a vertex is 1, 3, 5, 7, any odd number, such vertices will be either 0 or 2. So let's just go back. So in this case, in the first figure, in the first graph that we saw, here we could see that there are 2 vertices whose degree is odd, and we were able to draw this without lifting our hand. Only thing is that we started from city C and we reached at city A. So this is an example of Eulerian path, and this is an example of Eulerian circuit, because it completes the circuit. You come back to the same place. We had seen another graph here, so let's just try it out over here. So let's just see what is the degree of this city 5. There are 2 edges connected to city 5, so the degree is 2. Here city 3, the 1, 2, 3, 4. So the degree for city 3 is 4. Similarly, here it's 4 and here it is 3, because there are 3 edges connected to 2 and 3 edges connected to 1. So here again we are having 2 cities whose degree is an odd number. So the degree of 2 vertices are odd and rest are even, 2, 4, 4. So what we can do is we can start from any city. Let's say we start from 3 and then we go to 5 and then we go to 4 and then we go to 3 and then we go to 1 and then we go to 2 and then 4. But then in that case we are missing this this path from 2 to 3. So let me just draw it over here. So this is okay. So let's say there is a city here. This is one city 1. These are the cities. If I start from here 1, 2, if I go like this, and then if I go like this and like this, then so the middle cross is not happening. So I was here, I can do at the most here, but I cannot draw this cross. That is when I'm starting from here. So what I'm going to do is I'm going to start from a vertex which has got odd degree. So here I saw that the degree is 3. Here also I saw that the degree is 3. So I'm going to go like this: 1, 2, 3, like 4, 5, and then 6, 7, and 5. So I'm done. So we start from here and we are ending here. So this is an Eulerian path, and in an Eulerian path you can have, like I said, maximum 2 vertices whose degree is odd, and rest of the vertices the degree will be even. So we need to understand these things before we start exploring in yantras. So that is why I'm spending a little time on this. I think now we are good to go to the yantras. So let's do that. So this is a shape that we see in many yantras. It's in Sanskrit. It's called Shat Kona. Shat means 6. Kona means corners. So Shat Kona is a 6-cornered figure, or usually it's a hexagram constructed by 2 equilateral triangles. And in in Hindu mysticism or in yantras, this pink colored triangle which is upward facing, this upward facing triangle is called Shiva, and this downward facing triangle is called Shakti. So Shiva refers to energy and Shakti refers to matter. So with energy and matter we have the creation happening in place. So that is what it symbolizes, Shiva and Shakti. Now let's say that we have to draw this particular hexagram. So let us first think, can it be an Eulerian circuit? Can it be an Eulerian graph? So what should we check? So looking at a figure, if we want to know if it is an Eulerian circuit or if it is an Eulerian graph, the first thing that we need to do is find the degree of each and every vertex. So let's do that. So let's say that this is one vertex. So here the degree is 2 because there are 2 edges connected to this vertex. Similarly, 2 connected to this vertex and 2 edges connected to this vertex. Similarly for the other triangle. Now if we consider these vertices which are formed, or these points which are formed by the intersection of the 2 triangles, suppose we consider that also as vertices. Let us see. So now we are having how many cities? 1, 2, 3 cities in one triangle, 3 cities in the other triangle, so total 6, and we have a hexagon formed in between, so in the middle, so 6 vertices of the hexagon. So 6 plus 6, we have 12 cities. Now we have this problem of the postman going through all these paths, and he's going to all the cities and he's delivering letters to everybody along these paths. So this is what he is doing. So let's see from where we can start. Suppose we start from here. We go like this, and then like this, then like this. Let's say that we cover the outer part of the star without lifting our pen. So we are covering the outer part of the star, and we reach back here, but then we are stuck. We haven't gone through the inner parts. So let me just draw it. I think that will be better. So let's say that we start from a point and we do something like this, and I tend to draw the 5 petal star every time. So let me just draw uh, draw 2 triangles, and then we'll traverse it using a different color. Let's say that this is the triangle, and suppose we start from here. This is, it goes like this, and then like this, and then like this, like this, like this. Now if I join this, then I'm stuck because I have not gone through the inside. So what I'm going to do is I'm going to do this. So now I'm done. So we have verified. So here this every degree of each vertex, degree of each vertex was even. Each vertex. So when it is an even order, I mean when the degree of every vertex is even, then we can see that we start from a point and we end at the same point. So it's an Eulerian circuit. Yeah. And when will it be an Eulerian path? When there will be either, I mean this is also an Eulerian path, but Eulerian path need not be starting from the same point and ending at the same point. So it can be starting over here and ending at a different case. But that will happen when we are having two vertices whose degree is odd. Yeah. Now the most interesting thing which I feel is now this is we have figured out a path, but there is this question that always uh, I mean I find it very interesting. In fact, many of my students also find it very interesting. How many such paths exist? Let's say that these are all different cities, city 1 to city 12, let us say city 1 and then city 2, 3, 4, 5 and so on up to city 12. And if we have to travel through all these cities, through all these edges, in how many ways can we do that? This is one way. And maybe if somebody might say that, okay, this is instead of going like that, I'll take a different path. So let's say I start from the same city, but I don't go clockwise, I go anti-clockwise. Let's say I go like this, go here, I go here, yeah, here, here, here. So now this is a different path that I'm taking. Even though I'm traveling through the same paths, it's a different direction that I have taken. So this is a different path. It's not the same path. Yeah. So like this, now when we think about how many, it becomes a combinatorial question, and it's a very interesting question to think how many different paths that the postman can take. Because let's say somebody wants to find out where the postman is at a particular point of time. Can he really find out? Because there are so many different paths. So which path would he have taken? We don't know. So it would be very interesting if we can explore how many paths exist for this particular figure. Yeah. So we'll keep these questions in mind and then we will go ahead. So now I'll go a little quick. So this is another yantra. This is mainly called a mandala, where we have an in circle and a square which is circumscribed by the circle, and we want to check if this is an Eulerian circuit, Eulerian path, and then if it is so, then how many different ways are there to start from one point and traverse the entire graph. So let's just quickly check if it's an Eulerian uh, path or circuit. So this vertex has got two paths. This vertex where the circle is touching the triangle, this would have one path is over here, one is over here, one is this edge of this triangle and this side, so that here the degree is 4, here the degree is 2, here it is 4 and so on. And then we have the point where the square is touching the circle. So here there is one path, one edge here, one edge here, one here and one here. So here again the degree is 4. So as we can see, the degree of every vertex is even. So this has to be an Eulerian circuit. So now let's think how we can draw this particular, or at least let's try to figure out one way of drawing this particular figure. So I'll just draw the figure first. So this is the triangle, and here we have, let's say, this is a circle, and we have a square. Yeah. So let's say that we start from this point. We go like this. This is 1, 2, 3, and 4, and we go like this. And let's say I go like this way, here, and here. And now I can just go back. Yeah. So again, as you can see, I started from this corner of the square and ended at the same place. So again, this is an Eulerian circuit. Yeah, and that's also a. So we have answered that question. Is it an Eulerian circuit? Yes. Is it an Eulerian path? Yes. And the next question is, in how many ways can we cover this entire path, which is a combinatorial question, and some of us might find it very interesting to explore. So let's go to another few yantras. So this is again this particular circle with a lot of petals, when combined with an octagram, results in this particular shape. And here again we can see that the degree of this vertex is 1, 2, 3 and 4. So similarly, degree of every vertex in this circle will be 4, and here also there is 1, 2, 3, 4 edges. So the degree of every vertex over here is 4, and here also we can see that there is 1, 2, here 1, 2, 3, 4. So again this is an even order. The order of every vertex is even. So this has to be an Eulerian circuit. Same goes for this. And when we combine that, again, since the number of vertices are even, it will also result in an Eulerian circuit. But this would be a very complex question, trying to think from where to start and then how should we go about the path, and without lifting the pen, how can we traverse the entire thing, and how many ways can we do that would be a much more challenging question. Yeah. So okay. So this is the same shape which I constructed using the software. This is another yantra, Marana yantra. So I'm just repeating those questions again. First question, our interested question is this question an Eulerian graph? If so, in how many ways can we construct this particular graph? So here 1, 2, 3, 4. So the degree of this vertex is even, this vertex is even, this vertex degree is 4, this vertex 1, 2, 3, 4. Every other vertex is just like that. So this is also the same question. So what I observed is in all these yantras that we see, each of them is an Eulerian graph. Now, Eulerian circuit, I'm sorry. So can this be a coincidence, or can it be something, aesthetic? Maybe they were trying to draw these graphs using, like, the we call it rangoli in India, the colorful designs which are drawn with rice powder and stuff like that. So you draw it, and the ladies usually they hold this powder between their index finger and thumb, and then they draw it. So you start from a point and you draw the entire figure and you come back to the same point. Could that be one of the ways in which they were constructing yantras? That is something that can be explored. And I have 3 more yantras to show, which are very interesting. So this is one such yantra called Durga Yantra, and as we can see, there is a triangle which is pointing downwards, which is the Shakti triangle, and there are 1, 2 and 3 triangles which are pointing upwards. So there are 3 Shiva and 1 Shakti triangle, and they are, all the other questions remain the same. Can this be an Eulerian graph, Eulerian circuit? If so, in how many ways can we draw the graph? So in how many ways, for this question would be, I think the number would be very large. It would be very large because there are a lot of nodes, and even for the hexagram, the first double start thing, the Shatkona that we saw, for that also the answer is actually, it might look like, okay, it's a small figure, so maybe the answer is very small, but it's not that small. So I would really suggest that all of you try finding out how many such paths exist. And for Durga Yantra, those who really find it very interesting can explore it. But here from Durga Yantra, we get introduced to another way of exploration. So there was this mathematician by the name Penny Morris, who, what he did when he saw this yantra, he counted the number of vertices. So how did he count? He said that, okay, these lines and circles, they are meeting each other. So the points of intersection, he counted the points of intersection, and he found that there are 18 points of intersection, and he gave a number from 1 to 18 to each of these points. But he arranged them in such a way that if you add the numbers in any straight line, if you add 1 plus 14, 15, 15 plus 11, this will be 26, 26 plus 15 is 41. Let's try to add this. 16 plus 14 is 30, 30 plus 2 is 32, 32 plus 9 is 41. So if you add the numbers in any straight line, it will add up to 41. So he made this Durga Yantra into a magic figure. Now when I saw this, I was wondering, like, how could he have got the positions for these numbers? So a few of my students, we all, I just put them to task, and a couple of them are attending this session as well. So everybody started thinking how we can place these numbers, and I mean, everybody tried a lot, but we could not arrive at, we could not come to one particular assumption how he must have thought of these positions. Then we thought maybe he used the concept of parity, of odd and even. Maybe he counted the number of vertices. There were 18 vertices, and there are 1 to 18 numbers, in which 9 are odd and 9 are even. And if we are constructing a magic figure, the total, or the magic constant, as we say, in this case it is 41. So the magic constant has to be either odd, or the constant has to be even. So if we assume, let the constant be even, so when will the total of a line be even? So if we are having so let's take, suppose, assuming that the total of every line should be even, so then 1 2 3 4 5, there are 5 vertices over here. So 5 numbers, if the total should be even, then all of them should be even, or there can be 2 odd and 3 even, or there can be 4 odd and 1 even. So like that, with trial and error, it could be placed, because you see there is no specific pattern in which the numbers are placed. There is 1 here, 2 here, 3 here, 4 here, and 5 is here. It's not placed in a particular pattern, so he has used something. Another thing that we tried is using variables, like you use variables 1 to 18, so a to the 18th alphabet, and then you frame equations. So you will have how many lines? 1 2 3 4 5 6 7 8 9. So 9 lines, that is 9 equations, and we have 18 variables. So it's very difficult to solve 9 equations with 18 variables. I mean, 9 equations and 9 variables would have been easier, but then 9 equations and 18 variables is very challenging. So this we tried for a day, and we could not succeed much, but at least we got some kind of hint which we used in the next yantra. So this is a Navakonaka Yantra, which is different from Durga Yantra. Here in Durga Yantra you see a Shakti triangle and 3 Shiva triangles. Here you see 1 Shiva triangle and 2 Shakti triangles. So Nava means 9, Konaka means again corners. So since there are 3 triangles used, there will be 9 corners, and this is again, can we call this as an Eulerian circuit? If so, then how many ways are there for drawing the entire circuit? Is something that we can explore. And now we have another thing on which we can use for exploration. Now we can count the number of vertices, and if we count the number of vertices in this figure, it comes to 17 vertices. So if we use the digits, if we use the numbers from 1 to 17, and we try to place them in such a way that it becomes a magic figure, will it be possible? So that's a very interesting question, and we pondered over that particular question, and the answer that we got was no, it cannot form a magic figure. And we used a lot of logic for arriving at that particular answer, because again the logic was the same thing. The magic constant can be either even or odd. So we assumed if it is even, then here we are having 4 points, and if the total should be even, then either all the 4 should be even, or 2 should be even and 2 should be odd. And if this is, if two numbers are placed in this, two odd numbers are placed in this, what could be their positions? It could be in the corners, or it could be in between, or it could be one in the corner and one in between. And then we tried all such possibilities, and logically we could evaluate and take out. So when we are saying we, when I'm saying we, I'm referring to that group of students with whom I was working, and we found out that we cannot construct a magic figure using the numbers from 1 to 17, because there are 9 odd and 8 even numbers from 1 to 17. So this cannot become a magic figure. Yeah. But this will become again an Eulerian circuit. So coming to the last yantra. So this is a famous Sri Chakra, and it's considered to be the most difficult yantra to construct, and we can see a lot of triangles getting formed in between, and so this is a black and white form of that. Now let's try to see if this Sri Chakra is an Eulerian circuit. So we can do that very quickly. So here the degree is 1, 2, 3, 4. So degree is 4. Again here degree is 4, degree is 4, degree. So wherever the triangle is touching the circle, the degree is 4. And the corners of these triangles over here, where it is not touching the circles, the degree is 2. And the intersection points here, the degree is 2. Here we are having degree 6, here degree 4, here also degree 4. Similarly, when we see now, this is an Eulerian circuit. Now just think about it. How many ways could be there to construct this Eulerian circuit? Wouldn't that be an interesting question? For me it is. I really hope that this question would be interesting for at least some of you. And even, I mean, before even we think about how many ways are there to construct this particular Eulerian circuit, to figure out even one way would be really great. Yeah. And there are some people, like one of my students who was there in our group, his name is Ojas. When I showed this particular figure, this Durga Yantra, he saw this figure, and we were not discussing about graph theory at that particular time. Okay, we were just discussing about Yantra. When he saw this particular figure, he said that, oh, I think we can draw this particular figure without lifting our pen, I mean, and overwriting. So I think we can do that. So I was really zapped. I never thought on those lines till then. I said, how do you know that this can be done? So he said, well, I really feel it can be done. Let me just try. And this is what he did. He said that, okay, I'll do something. I'll have to, yeah, let me just think about it. Yeah, okay. So he did something like this, and then like this, and yeah, from here till here, and no, he didn't. Oops, yeah, he didn't go from till there. He went till here, and then he constructs this particular triangle, and he comes back and he goes here, and then he constructs the circle which touches all the vertices. So he did that. It was something very natural for him, and he got this very intuitively. So I was really surprised how he did this. So he said that, okay, I have done such kind of questions. I mean, I have explored where you see a figure and then you try to draw that figure without lifting your hand. So now I feel that these kind of yantras, wouldn't it be really good if we can introduce this to students at a very young age and give it as a puzzle for them, so that they can try exploring, and maybe when they grow up, when they see a particular figure, they can intuitively say whether it's an Eulerian circuit or an Eulerian graph. And what I really found interesting is that all these yantras that we discussed, all of them are Eulerian circuits. So is it a coincidence, or is it something more than that? So with that, I'll take a pause